consideration now. Substrate's the most important, by the way. That's why I did it first. The substrate is also the easiest for every single one of you in this room following this lecture to understand. You can easily all at this point identify tertiary, secondary, primary. Now we have a new trend. It's a little different than our previous trends for radical stability, carbocation stability, but big is bad, small is good, fast, big is slow, however you want to say it. But we have a very easy thing to understand reactivity. The second consideration is going to be the nature of the nucleophile. First, we talk about substrate. Second, we're going to talk about the thing the substrate reacts with, and this is called our nucleophile, and we're going to explore its nature. Okay? Nucleophiles, phile from the Greek word philos for love. Nucleo must be nucleus, so nucleus-loving. Nucleus-loving species must have electrons available for sharing or forming covalent bonds. So to be a nucleophile, it has to have some electrons that it can share, but our ultimate goal here will be to form a covalent bond. So nucleophiles will be forming covalent bonds with things that are missing electrons. So has to have electrons, has to want to share them. So electronegativity is the desire for a species to want electrons. Electronegativity is opposed to nucleophilicity. Electronegativity and nucleophilicity are opposite trends. An electronegative atom wants to hold on to electrons, doesn't want to share them. Nucleophiles have the opposite feeling. They want to share electrons. They're not holding on to them tightly. Okay, so this is kind of just, if we know something about electronegativity, and we know that nucleophiles are going to be species that want to share their electrons, if we know how to identify an electronegative atom or a non-electronegative atom, then we should be able to identify a good nucleophile or a poor nucleophile. And so, in the periodic table, I'm just drawing this from memory here. We know that electronegativity increases from left to right or bottom to top, fluorine being the most electronegative, being more electronegative than oxygen or chlorine respectively. So if we go up any column, we increase in electronegativity. If we go across any row, we increase in electronegativity. Nucleophilicity is opposed to electronegativity. Fluorine really wants to hold on to its electrons, does not want to share them to make bonds. Iodine has electrons, not very electronegative, very easy to make bonds. Fluorine, again, very electronegative, doesn't really want to share its electrons even if it has them, but carbon, if it has electrons, would love to form bonds with them because it has them available, they're not being held tightly. And so this particular trend here, that nucleophilicity is opposed to electronegativity, is a very good general trend for us to understand. If we were to apply it, if we had F minus, Cl minus, Br minus, and I minus, this would be the strongest, this would be the weakest. Okay, this is the first bit about nucleophilicity. This is the most important one. So we're going to look at 3 different things to consider. This will be part A. If we were going to go down a column in the periodic table, if we were comparing hydroxide to thiolate to selenate This would be the best nucleophile. This would be the worst, if we were just comparing these three amongst one another. So the periodic trend, the first one we're going to look at, we'll just call it A, most important for you to understand about nucleophilicity. So if we're comparing any of these, we know right away what to do. If we're making some comparison between nitrogen, oxygen, and fluorine, we know right away to do here. The second part that we're going to consider, we'll call it B. And we're going to say when pairing. Identical atoms, negatively charged, nucleophiles are stronger or better. So when we're comparing identical atoms, a negatively charged nucleophile would be stronger than a neutral one. So negatively charged nucleophiles are stronger when comparing identical atoms. Here's what I mean by this. If we're comparing these two molecules, the nucleophilic atom in both cases is obviously oxygen. It has electron pairs to share. Hydrogen does not. So if we were reacting some substrate with these two nucleophiles, one would be much faster than the other. One would be much more reactive than the other. Same substrate, comparing this hydroxide versus water. This would be the stronger or faster reacting nucleophile when comparing two of the same atom. Okay, so if we come under this comparison, or we need to make a choice, if we want to install an OH group on a substrate by a substitution reaction, and I say, well, what would your nucleophile like to be? This wouldn't be your best choice. This would be your best choice. Or comparing these two, this would be the best. The third one is different than this. And when we apply these, A, B, C, let's just use A first. If we can use it, great. It's the easiest to understand. B is a subset of A when we have the same atom. And C is a subset of B and A. All right, so we don't always use this one. But sometimes we might. Let's say when comparing identical atoms with identical charge, we might occasionally compare two nucleophiles that have the same atom and the same charge. Let's compare acetate with hydroxide. Here's what I mean. In both of these nucleophiles, we're comparing oxygen. Charge is the same. So we can't use this trend. We can't use the periodic trend because it's the same atom. So when we get down to this type of comparison, which will be the more powerful nucleophile, the stronger base is the more powerful nucleophile. But be very, very careful. In this case, the stronger base is the more powerful nucleophile, but it only applies to this particular case where we're comparing the same atom with the same charge. The overwhelming principle, and I'll bring the slide back momentarily, the overwhelming principle about nucleophilicity is that it's opposed to electronegativity. So if we can make this type of distinction, we don't look at condition B and C. If we get to a situation where we're comparing two identical atoms, only then do we think about charge. If we get to a situation where we're comparing the same atom, same charge, then we have to switch to a more refined notion that the stronger base is the more powerful nucleophile. I know this is confusing. Students are always going to want to go to this one first. Don't. Simply follow these through. The most important one is the one we spent our time on first. Part A, periodic trend, understanding electronegativity to our advantage. The second trend, we have negative charge species. They're more willing and more reactive and more desirable to react with something to make a stable bond. When we have two species, same charge, you have to look at the overall molecule and understand which one's the stronger base. For these two, you should very rapidly be able to figure out that hydroxide is the stronger base than acetate. The way that you could easily do that is simply draw the conjugate acids of these two things, water and acetic acid. pK of acetic acid is about 4.75. pK of water is about 15.7. This is the weaker acid. This will be the stronger conjugate base. So using acid base and your knowledge of it can always get us to an understanding here of basicity. Sometimes you just simply have to apply conjugate acid principle to it to relate back to it. So that wraps up the nature of our substrate, the nature of our nucleophile.